This video is on the objective solving trigonometric equations using fundamental identities. So hopefully you remember all of your fundamental identities. I'm not going to be listing them all again here, but you have those reciprocal identities, quotient identities, Pythagorean identities, even odd identities, co-function identities, the sum and difference formulas, double angle formulas, half angle formulas. And I think that was about it. So, I'm hoping that you have those down before we get into solving equations where we can use some of these identities to help us, simplify the equation. Alright, so if you'd like to see more, about the topic, click on More Instruction, see their videos, their examples, their notes, and hopefully those help you. Alright, so we're asked to solve the following equation for beta. But, like you've seen in previous assignments, previous objectives, if one of these trigonometric equations has a solution, it's going to have infinitely many. But they don't want all infinitely many, right? They just want the solutions that are between, the values of beta that would make this statement true. They just want the values of beta from negative pi to pi, but just not including pi. Alright, so now every time I use an identity, I'll write down, what identity I'm using. So here we have this equation. On the left side there's a fraction. The numerator is secant squared beta minus 1 divided by the tangent of negative beta, and we're asked when is this equal to negative square root of 3 divided by 3. So this is a pretty hairy looking equation. You got some fractions and roots. There's two different types of trig functions here. But one thing I'm noticing, and one thing to look out for, whenever you see a trig function squared, there's a good chance you can bring one of those Pythagorean identities into play. So the one in particular I'm thinking of is the one involving secant squared and tangent squared. Hopefully this rings a bell, right? Remember the tangent of some some angle squared, say the tangent of beta squared, plus 1 would be equal to the secant of that same angle, to the second power. So that means that secant squared beta minus 1 is equivalent to tangent squared beta. Alright, so I'm going to make this substitution, I'm going to make this replacement in a second. Also, not only do I want to have the same functions involved, right? If I replace secant squared beta minus 1 with tangent squared, then it'll be all just tangent that shows up in the equation, which is nice. But also, I would like the same angle measures. This has an angle measure of beta in it. This has an argument or an angle measure of negative beta. I don't like that they're different. But hopefully, again, you recall how to rewrite an expression with a negative argument in terms of a positive argument. And that was with those even-odd identities. And again, the one in particular is the one involving tangent, right? The tangent was an odd function, meaning that the tangent of negative beta is just the opposite of the tangent of beta. All right, so I'm going to make these two replacements. I'm going to replace secant squared beta minus 1 with tangent squared beta, and I'm going to replace tangent of negative beta with negative tangent beta. All right, so this is using the use of the fundamental identities. All right, so now this left side becomes this. The numerator is now tangent squared beta. The denominator is now negative tangent beta, using that even-odd identity. And then the right side is just that number still, negative square root of 3 divided by 3. Alright, so some things I'm seeing. We can multiply both sides by negative 1, get rid of those minus signs. Right, the negative there, then both sides will have a positive coefficient. And then I'm noticing a factor of tangent in the denominator, and two factors of tangent in the numerator, so one of those will cancel. And after doing those, I'm left with just tangent beta on the left equals, and then positive square root of 3 over 3 on the right. So we've taken this crazy looking equation and through some use of identities, transformed it into a much simpler linear equation with just tangent now. Okay, and then remember, when I have a linear equation with one function, I get that function alone, which it already is, and then I just think, once around the unit circle, going counterclockwise, think once around, what are some angles that have a tangent of square root of 3 over 3, right? Well, one of those was pi over 6, right, 30 degrees, and just add pi to that. The other one was 7 pi over 6. But really, I could describe all the solutions here as pi over 6 and then plus any multiple of pi, right? I just keep going halfway around and I'll land at another angle that has a tangent of square root of 3 over 3. And the reason I can just add multiples of pi is, this is the tangent function, and remember the period of tangent was pi. It repeated every pi radians. So I can describe all the solutions to this equation this way, as pi over 6 plus pi times k, where k is some integers. So take pi over 6 and add or subtract any multiple of pi. Pardon me. Alright, so there's a description of all the solutions, right? Infinitely many of them. But we don't want all of them, right? They just want the solutions that are between the, negative pi and pi. So I'll start listing some. Here's a list of some solutions to this equation. Now when k is 0, just pi over 6. Right? And going in this direction, I'll just be adding pi, right? It's k times pi. So I'm just, every time I increase k by 1, I'm increasing the solution, getting a new solution that's pi bigger. Now if I get a common denominator here, that's, 6 pi over 6. Right? And going this direction, I'll be subtracting pi to get other solutions. Alright, so pi over 6 is one solution. Pardon me. Adding another pi here, 6 pi over 6 would be 7 pi over 6. Alright, that's another solution, as you saw in my drawing here. Keep going, you got 13 pi over 6 would be another solution, and so on. Or going in the other direction, right, subtracting pi, subtracting 6 pi over 6 from this solution, you get negative 5 pi over 6, negative 11 pi over 6, and so on. So there, I just gave you 5 solutions to this equation. But they don't want those, right? They don't want all of those. We want solutions that are in this range. Alright, and these, I should say beta equals any of these are solutions. We only want values of beta from negative pi to pi, or negative 6 pi over 6 to positive 6 pi over 6. So the only ones of these that I'm looking at here that satisfy this inequality are pi, pi over 6 is in this range. Then all these are too big. 7 pi over 6 is bigger than pi. 13 pi over 6 is bigger than pi. Negative 5 pi over 6 is okay too. That's in here. That's between negative pi and pi. But then negative 11 pi over 6 is too small. So the only two solutions coming out of this are pi over 6 and negative 5 pi over 6. Those are the only ones solutions that are in the range that they wanted, which is that third option there. So again, hopefully you saw me use a Pythagorean identity, one of those even odd identities here, and they're showing you the same stuff, right? And then what the equation becomes, right? Exactly what I wrote out on my paper. Alright, so hopefully watching me do this, looking at the more instruction, reading the answer explanations when they come up, hopefully all this stuff helps you out when you're working on this on your own. And just because I used one particular Pythagorean identity and one particular even odd identity doesn't mean you're going to see a problem with those. You might have to use other identities, so you're going to have to go back and refresh your memory as to what all the all the identities you've learned are. Right? Again, reciprocal, quotient, Pythagorean, even odd, cofunction, sum and difference formulas, half angle formulas, double angle formulas, all that stuff, right, is going to come into play in some of these questions. So again, hope this helps. Thanks for watching.